This recording is a repeat of the talk I gave at Supercomputing 2015. I'm Mike Rainey, and my co-authors on this paper are Unordered and Arthur Chargeron. A graph-traversal algorithm is any algorithm in which computation proceeds from one vertex to another through the edges in the graph. So why are we giving special attention to such algorithms? Well, we do because graph traversals play important roles in algorithms and computer systems, and if we can improve the performance of graph traversal, we can automatically improve the performance of many algorithms that depend on graph traversal. The particular challenge in parallel graph traversal is coping with the irregularity of graphs. Irregularity means that it's easy either to parallelize too aggressively or not enough. The subject of this talk is a new technique to address this issue, for the case of loosely ordered traversals over any directed graph. In the study, we assume a multicore platform with a set of dedicated cores and as input a directed graph that is laid out in RAM in the textbook adjacency list format. Our main contribution is a new graph traversal algorithm, and our analytical results show that our algorithm is work efficient, which means that parallelism related overheads are well amortized, and it means that our algorithm delivers a high degree of parallelism. On the practical side, we show that our implementation competes well with state-of-the-art graph traversal algorithms on a machine with 40 cores. In the literature, a lot of attention has been paid to breadth-first traversal, but there's relatively little attention paid to depth-first, or DFS. The reason probably has to do with the fact that DFS is known to be p-complete, which suggests that it's hard to parallelize. But it turns out that the strict lexicographic ordering of DFS is not always required by applications. One can often use a traversal that is DFS-like, giving the advantages of DFS, while achieving high parallelism by relaxing the ordering requirement of DFS. Some applications that use DFS are parallel garbage collection, graph reachability, graph search, and so on. Also, there's at least one graph processing framework that uses parallel DFS to speed up large graph computations. So when it can be used, the loosely ordered parallel DFS traversal is usually preferable because DFS is usually faster than alternatives such as BFS. But to explain why, I need to tell you exactly what this pseudo DFS algorithm is. From now on, I'm going to refer to pseudo parallel DFS as PDFS, like in the paper. In PDFS, we are given as input a directed graph and the identifier of a source vertex, and our objective is to determine the set of vertices that are reachable from the source vertex in that graph. To track which vertices have been visited so far, all the cores share an array of flags. PDFS uses this array to guarantee that each vertex is visited at most once. To track which vertices are ready to be processed, PDFS uses a data structure to store the frontier of the traversal. The frontier is distributed in pieces among the cores, and each core owns one local piece. When it owns some vertices, a core pops a vertex from its frontier and tries to gain access to visit the vertex. If the vertex is not yet visited, then the core uses an atomic test and set operation on the corresponding cell in the array of flags. If the operation succeeds, the core visits the vertex by pushing into its own frontier all the neighbors of the vertex. When it runs out of vertices in its own frontier, a core tries to find work in the frontier of another randomly chosen core, just like in randomized work stealing. Now we have some intuition for why PDFS is faster than PBFS. On the one hand, PDFS doesn't require performing synchronization between every two levels, whereas PBFS does. Because of this property, PDFS is sometimes called an asynchronous traversal whereas PBFS is called a synchronous one. There's another reason PDFS is sometimes preferred. In parallel marked sweep garbage collection, PDFS is preferable because PDFS visits heap objects in mostly the same order that the heap objects are allocated in the heap. However, perhaps one reason why PDFS is not as widely used as it could be is because of a performance issue that we're going to look at now. In any parallel algorithm, including PDFS, there's an important trade-off that has to be made on a regular basis, and it's a trade-off between the cost of migrating some chunk of parallel work and the benefit of the parallelism that could be achieved by the migration. If you pay too much for useless migrations, then the traversal is going to be slow, but if you migrate too rarely, it'll be slow. That's why efficient parallel algorithms tend to find a balance between these two extremes. The usual name for this problem is the granularity-control problem. Effective granularity control is particularly challenging in PDFS. The reason is that when the algorithm migrates a newly discovered piece of the frontier, the algorithm lacks information on the future. That is, the vertices in the frontier could lead to a large region of undiscovered graph with lots of opportunities for parallelism, or they could lead to a dead end with none. Because of this kind of unpredictability, it's not obvious just how to design a PDFS algorithm that can avoid creating too many pieces of work, or too few big ones. We can see the challenge more clearly by considering some input graphs. Looking at this first sample graph, we can see that two cores could ideally traverse the two chains in parallel and in doing so gain some speed up. But to realize this parallelism, PDFS has to split a frontier which stores just two edges and then migrate one of the vertices to another core. The trouble is that, in general, splitting such small frontiers leads to unacceptable overheads. This second graph shows us why. Assume core 1 begins its traversal with source vertex S, sends vertex B to core 2, and continues working on vertex A. Soon enough, core 1 runs out of work because A has no outgoing edges. By this time, core 2 has processed B and has a frontier consisting of C and D. So it sends D to core 1. Soon enough, core 2 runs out of work, and now we're back to the same situation as we were in the beginning, because this time with D is the new source. So this graph shows that systematically splitting small frontiers can lead to a large number of communication operations. Just to summarize, the two graphs we just considered here are worst-case graphs. So just how big of a problem does it represent in general? Well, if we can assume small world, it seems like we might not have a problem. But applications such as parallel GC have to deal with many different graphs, including ones like this, possibly. For instance, long chains are generated by programs that build long linked lists and have to be traversed by the GC. Previous approaches to PDFS deal with granularity control by using a heuristic called batching. A batch is a small buffer that stores a part of the frontier. In a version of PDFS that uses batching, each core is assigned a concurrent work-stealing queue. Each queue stores pointers to batches. Also, each core has assigned to it one special batch for private access. The private batch can be accessed efficiently because the accesses are all single-threaded. Cores perform load balancing by stealing the oldest batch from the queue of a randomly selected core. Kong et al. Observed that a simple batching technique can easily kill the amount of parallelism that can be exploited by the graph traversal. To see why, consider what batching would do with our first example graph, the one with the long 2 chains. In that graph, batching sequentializes the entire traversal, assuming that the batch size is at least 2, which is a safe assumption. To address this issue, Kong et al. Proposed an additional heuristic to allow partially filled batches when there are cores that are idle. However, to the best of our knowledge, none of the batching algorithms so far provide strong guarantees on the overheads batching is designed to control. This situation is unfortunate because parallel BFS enjoys analytical bounds that rule out worst-case behavior for all graphs. So, in this work, we ask whether PBFS can be put on the same footing. Our first analytical results show that our PBFS is work efficient, which means that the running time of PBFS is the same as that of the best sequential algorithm, at least up to constant factors. Our second analytical result shows that our algorithm delivers close to optimal parallelism, which means that it can parallelize even the 2 chains graph that we saw in our first example. And through experiments, we show that our PBFS leads to a competitive implementation. To back this claim, we show the results of a performance study comparing state-of-the-art algorithms. We also show that our PBFS keeps one of the properties that makes DFS popular, the ability to exploit data locality. In our algorithm, work migration is implemented by a message passing through shared memory. Each core regularly checks on the status of a work request cell. So when core 1 wants to request work from core 2, core 1 writes its ID into the request cell of core 2 and waits for a response. We give each core exclusive access to its own frontier. Thanks to this private access, we don't have to worry about designing a concurrent data structure. We can instead focus on finding a fast single-threaded data structure that does the job. The technique we use to address granularity control is based on amortization. When receiving a query, a core shares its work only if one of the 2 following conditions is met. The core can share its work if it has a frontier larger than some fixed constant k, or the core can share if it has already treated more than k edges since the last time the core shared work. The first condition ensures that a core can immediately share if it has enough work in its frontier. The second one enables a core to control migration overheads when parallelism is scarce. Regarding the specific value of k, we pick a setting depending on the target machine, so that treating k edges is enough to amortize the cost of any migration on that machine. On our target machine, we found that setting k to 1000 roughly gave best results. Now let's consider how PBFS deals with our first sample graph. Even though the core that starts on this graph will have no more than 2 vertices in its frontier, our PBFS will still manage to migrate one of the 2 vertices eventually. In fact, it can after treating just k edges. Recall that the problem with that second graph is to avoid migrating a vertex at each step, or too many steps in general. What's going to happen here is the core is going to migrate 1 vertex for every k steps. Each migration is therefore amortized on the previous k edges. In summary, this technique allows our PBFS to share work even as small as a single edge, while still amortizing the cost of migrating work. Our technique can amortize either on the work being shared, which is work going to be performed in the near future, or it can amortize in the amount of work performed in the past. This combination of strategies enables our algorithm to achieve high parallelism and work efficiency at the same time. This slide shows the pseudocode of our algorithm. On the top, we see that our algorithm has tuning parameters k and d. The parameter k we've seen already, and the parameter d is an integer which controls the frequency of polling. Both of these parameters are platform specific, but they can be picked offline with some easy tuning. In PBFS, each core runs the loop on the left. If its frontier is empty, the core goes into a loop where it queries other processors for work. When it has some work, the core first checks for a request for work from another core. After that, the core proceeds to pop a vertex v from its frontier. If it wins the race to v, then the core pushes the outgoing neighbors of v into the frontier, and then it pops v. To handle a work request, a core checks whether it has work to send, whether it has a pending request, that is, using the technique we described in the previous slide. After this conditional, the core transfers any vertices it can directly to the frontier of the core that made the request. Now we're ready to state the analytical results. The first one says that our PBFS performs at most 3 times m over k migrations, where m here is the number of edges in the input graph. This bound means that each work migration is amortized over at least k over 3 edges. The second result shows that the total amount of work performed by our PBFS is linear in proportion to the size of the input graph. This bound establishes the work efficiency of our PBFS. The final result shows that in our PBFS, each core responds to a work query in order d plus log n time, where n is the number of vertices in the input graph. This bound means that our algorithm can exploit nearly all opportunities for parallelism up to a small delay. There's one remaining component of our algorithm that I need to mention, but only briefly here. It's the data structure that we use to represent the frontier. This structure is critical for performance because the frontier is accessed very often during the traversal. We based our frontier data structure on a sophisticated tree data structure that we developed in prior work. This tree data structure gives 2 key features. First, our frontier can push and pop in constant time and still be as fast on average as a fast resizable stack data structure, say like the STL vector. Second, our frontier can divide in half in logarithmic time based on the out degrees of the vertices in the frontier. So let me explain a little. In the diagram on the right, we see a frontier that contains vertices A and B, and implicitly their out edges C through H. Performing this edge-balanced split on this data structure ends up dividing the frontier into 2 new frontiers, each with equal numbers of outgoing edges. Does this by dividing the edges of the vertices as necessary. Our frontier gives us exactly what we need to migrate large pieces of work efficiently and to efficiently parallelize high-degree vertices. This plot shows the main experimental results. On the y-axis, we have speed up of parallel versus sequential DFS. So there, higher means better. The black bar corresponds to our PBFS, dark gray to the PBFS of Kong et al., the light gray to the parallel BFS algorithm provided by the problem-based benchmark suite, and the white bar to Ligra. Let's start by comparing our PBFS and Kong's. Ours is the same or faster for all graphs except one synthetic graph. The situation is the same for PBFS. This one exceptional graph is a perfect binary tree, which is a bad case for PBFS because its structure, the structure of the graph, is well suited for a BFS style traversal. Our PBFS shines on high diameter graphs and graphs with little or no parallelism, which appear on the far right. This latter result shows that PDFS is just 20% slower than sequential DFS, even in the worst case for PDFS, where in fact there are no opportunities for parallelism at all. On small world graphs, our PDFS is faster than the others, except for LIGRA, which is an algorithm that is designed specifically to target small world. LIGRA can outperform PDFS on small world graphs because LIGRA uses some sophisticated heuristics to skip the processing of a large fraction of the edges. The other algorithms always process all of the edges. Various batching techniques were proposed for PDFS over the years. Our PDFS introduces the use of amortization to bound these costs, the migration costs. The most closely related work on parallel BFS is a study by Leiserson and Schardel. Their algorithm and ours enjoy similarly strong analytical bounds, but our PDFS provides the advantages of DFS-like traversal. There are a few recent PBFS algorithms that optimize for small world graphs. These algorithms perform well on small world, but degrade significantly on high degree graphs, or graphs with high degree vertices. It would be interesting future work to look for a PDFS which can exploit small world graphs in a similar fashion. Finally, the KLA graph processing framework uses a hybrid between PDFS and PBFS to achieve speedups over other frameworks which use just PBFS. In summary, we presented here a new DFS algorithm to accelerate traversal of in-memory directed graphs. We raised PDFS to the same level of analytical rigor as PBFS by establishing key efficiency theorems. We conducted an experimental study to show the performance trade-offs between our algorithm and other state-of-the-art algorithms. In our paper, you can find additional experimental results which show that our PDFS can exploit data locality as effectively as sequential DFS. Overall, the results show that our PDFS achieves high performance in theory and in practice, and may provide a useful component for other algorithms and graph processing frameworks.